lunchtime far away, you guys probably consume, let's say, a can of pop. So let's say Coca-Cola or whatever it is. Now, if you were to do that and you were to actually consume it, yes, it would be very delicious, but very shortly afterwards, you would die. Now, why is that? Why would consuming something like a pop cause such a terrible, terrible thing to you if, in this case, you have no buffer? So in this case, let's take a look at you, the makeup of you. So once upon a time in a science class far away, you guys learned that you have something in your cells or the nucleus called DNA. Okay? Now, in terms of where the DNA is concerned, you guys learned that, oh, well, you've got A, C, G, and let's say T, and then you know that it is partnered up, so you have the pairings that look like this. Yes? Now, the question here is that you knew that they were kind of like stuck together, but what is the nature of the thing that causes the two strands to actually stick together? Hydrogen bonds. Okay? Now, you guys also learned that through a system of tRNA and mRNA, what happens is that the DNA goes ahead and it makes a whole bunch of strings of amino acids. And you guys learned that these amino acids, so this is your primary structure, and then this is like your secondary structure. And what happens with your secondary structure is that they fold together, and then your tertiary structure, I think, and then what's your tertiary structure? And then there's a quaternary one. But anyways, you know that eventually what happens is you get two of these chains that have amino acids, and they're all folded together, and then what happens is that they stick together. So the question is, what causes them to fold together? Hydrogen bonds, right? And then what causes like two different chains to actually stick together? Hydrogen bonds, okay? You also learned that inside your cell, you have this little funny looking thing, and you guys have all learned it. It's your mitochondria. And what is your mitochondria? Oh, don't tell Mr. Cooper this, or else his eyeball starts to twitch. Yeah, this one here produces ATP. Do you guys know how it produces ATP?
Glucose.
Huh?
Glucose.
Yes. And? So have you guys heard of the electron transport chain?
Yes.
Right. And that happens here because there is a difference between the concentration of the H plus on one side of the membrane compared to the other. And as the H's try to pass through the membrane, it now ends up donating and receiving electrons, and that is what is responsible for producing ATP. Now think about this. If you now take your pop, and your pop is now full of acid, because you've all heard that pop is acidic. Now you flood your cells with lots and lots of H's over here. What do you think that is going to do to your hydrogen bonds? It's going to disrupt them, isn't it? And then basically your DNA will become a tangled mess because they are now sort of not held together in an organized system. So first of all, then your DNA goes wonky. Okay? Number one. So number two. It now floods all your enzymes over here, and when it floods your enzymes over here, what is it going to do? It's now going to interfere with all of those hydrogen bonds, and then what's going to happen to all of your chains? It's going to denature, right? Now, here's the question. How many of you guys know about marinating your food? Okay, when you marinate your food, what is one thing that you put in your marinade all the time? Put in an acid like lemon juice or a bit of vinegar, or if it's a more delicate protein, it'll be like yogurt or something like that. Why? Because the acid tenderizes the protein, right? So this is why if you guys were marinating meat is a very tough protein, you can marinate it for 24 hours. okay, with a fairly strong acid, and then when you cook it, it's very tender, right? But if you have something like a fish, like halibut or some sort of a white fish, it's not a very dense protein, so if you actually use too strong of an acid and you leave it on for too long, it basically turns that protein into mush, right? So there's no more texture left. So what ends up happening is that you're breaking down the hydrogen bonds that are holding the protein structures, that are holding the enzymes, and then that basically causes the proteins to just kind of like unravel and the meat loses their integrity. And if it starts losing their integrity, you would say, oh, it's been tenderized, but if it is over marinated, now it's just mush, okay? And then over here, what happens is that if you've got too much acid, now you're basically ruining the difference in concentration between the inside and outside of your mitochondria. And if you're now ruining that concentration, what does that do to your electron transport chain? It basically destroys it, and then what does it do? It basically destroys your ability to produce ATP, and you die. So in all of these things over here, what the buffer system is doing, it is maintaining a constant pH in your system so that you actually are functional at a cellular level. And so in this case, you have your weak acid and conjugate base. You recognize your weak acid conjugate base right here. And so in this case, you would have your H2CO3 plus H2O giving you HCO3 minus plus H3O plus. Do you guys see this equilibrium? So now it says over here in point number 2, buffers work due to the fact that they contain acid species to neutralize the OH and a base species to neutralize the hydronium. So how does that work? So if you were to drink a pop and you now flood your system with a lot of acid, this concentration goes up, doesn't it? And when it goes up, what does my equilibrium do? It shifts to the left, thereby bringing down the hydronium ion, isn't it? And thereby keeping your system constant, right? What's that word that you use? Homeostasis. If you by any chance now consume lots of OH and this concentration goes down, what is going to happen? Equilibrium is going to shift to the right. So this is your acid species now providing the H plus to now maintain the hydronium ion, or if there's too much acid, then this base grabs the extra H pluses to now basically absorb it and reproduce its weak acid form. Do you guys see that? Okay, so this is what we mean by having an acid and a base to take care of too much acid or too little or too much base. Is that making sense to you guys? So this is why I really like this part, because it really serves to help you sort of understand what's actually going on in your body. And Yusuf's awake for the first time the entire semester. So when you go over and talk to Mr. Lockwood, be like, I learned about buffers, Mr. Lockwood. Okay? So now when you take a look at a buffer, remember it needs an acid species and it needs a base species. So over here is my CH3COOH. Do you recognize this as a weak acid? Now when you take a look over here, technically, when I add this, this is not a base. This is actually a salt. Do you see that? But contained within that is my conjugate base. So do you see how it's pulling in salts? It's pulling in weak acids and conjugate bases. So now you take a look at this one. What is NH3? It's a weak base. And then you take a look at the entire thing. The entire thing is a salt, but what can you tell me about the NH4? It's the conjugate acid. Okay? So you're going to need the weak acid, you're going to need the conjugate base, and then you're going to balance them out. Okay? And the equilibrium is what allows you to achieve homeostasis. Okay, so now let's take a look over here at the following question. So again, when we take a look at this, the question would be, what am I working with? So I am working with a buffer. Okay, it's telling you that. So from there, this one over here is going to be my weak acid. Over here, I give you sodium lactate, so the whole thing over here is a salt, but this part over here is my conjugate base. So the very first thing that we take a look at is, what am I working with? And I would say that I am working with a buffer. So therefore, you need a weak acid and a conjugate base in there. So part of your job is to figure out what they are. So the second question is, what is the equation? Now, I'm going to write this wrong. I'm going to write the wrong equation right now. Because in your head, you're thinking, okay, here's my acid. Here is my conjugate base. So acid donates, base receives. So you're going to probably write it in this way. HC3H5O3 plus C3H5O3 minus. Weak acid, conjugate base, so doesn't this donate? And then now you're going to get HC3H5O3 plus C3H5O3 minus. Does it make sense? No, it's kind of like this. It's kind of like if I had a calculator on this hand. I'm going, this one goes, oh, can I have a calculator? Oh, look, I have a calculator. This one's like, I don't have a calculator anymore. Oh, look, here's a calculator. Right? Or if I have like $10 in here and I'm like, I want $10, I slap it in, oh, I have 10 bucks, I'm rich now. And this one goes, I want 10 bucks, I slap it in, oh, look, I have $10 here. Is it really doing anything? No, this is like a circular argument. It goes nowhere. So I'm leaving this in here. This is the wrong way to set it up. The correct way to set it up is the weak acid and the conjugate base have to be on opposite sides of the arrow. So here I'm going to have HC3H5O3 plus H2O in equilibrium with C3H5O3 minus plus H3O plus. That's the only way that you now have this H3O plus, which you can adjust. So now that I have that, I do my ICE. And then I plug in my values. And in this case over here, if I'm plugging it in, notice currently I have two values. One is going to be for my weak acid, and one is going to be for my weak base, and then 0 for the hydronium. So this is like your common ion, because you have something on either side. Which direction will my equilibrium shift? Which direction will my equilibrium shift? It will shift to the right side, because why? Yep. Well, I'm more acid, but there's something a bit more tail, because even if I did this, so I'm just going to change this up. Even if I did something like this, and I do something like this, my equilibrium will still shift to the right. Gazel.
Because like you want to make H3O.
Yeah, because I have 0 H3O here, right? So therefore, I have no choice but to go. So good work. So over here, I'm just going to change this back. And then so now I'm gonna go ahead and go minus x plus x plus x. And then I go 0.12 minus x, 0.10 plus x, and x. So I am told here that my Ka is 1.4 times 10 to the minus 4. Is equal to 0.10 plus x times x all over 0.12 minus x. And now in this case over here, if you were to take a look, to avoid quadratics, the bottom x over here I'm going to say is very small. And the top x here with that initial concentration is also very small. Go 1.4 times 10 to the minus 4 times 0.12 divided by 0.1. And my x over here is 1.7 times 10 to the minus 4. This is the hydronium ion. And then so pH is equal to negative log of 1.7 times 10 to the minus 4. And I get 3.77. Now my emphasis to you is this the hard part? The answer is no, because once you have your ice chart, everything is easy. So what's the hard part here? The hard part is identifying your buffer and figuring out the weak acid conjugate base combination or weak base conjugate acid combination, and then coming up with the correct equation. Okay? So that's the important bit. This you have done a gajillion times. So therefore, I have every confidence you know how to do the math. It is the setting up that is going to be challenging. So, to finish up, can you guys please do number 17?
I don't know how to do chemistry anymore. What? Was it C6H5Cl?